the integration that we can have take into account the current aims of if we think about recovery plan, next generation EU funds. So in order to to consider targets for the improvement of the cities through new appraisal and evaluation techniques, or also to systems that concern risk simulations, as in this workshop, and security residency smart centers. So let's see the paper. Actually, we had 4 works for research. I read very quickly the title. The knowledge phase of the strategic programming, the case study of the Ionian valleys of Peloritani, Sicily, Italy. The impact of corrosion on the seismic assessment of reinforced concrete bridge piers. Seismic risk simulations of a water distribution network in southern Italy. Security and residence in small centers of island areas. Okay. So we can start. I don't know if we have someone for the first research. No. For the first research, okay. So I think that there is not someone for the second one, because Alessandro Razzulo sent an email. Nobody could present this lecture, so I think that we can start with the seismic risk simulation of the water network in southern Italy. The work was carried out by Maurizio Pollino, Antonio Di Pietro, Luigi Laporta, Grazia Fattoruso, Tonia Giovinazzi, and Antonia Longobardi, and the lecturer is Professor Maurizio Pollino.
Okay, good morning to everybody. Thank you to the chair for the introduction. My name is Maurizio Pollino. I am a researcher at the Enea APIC lab. APIC is the Analysis and Protection of Critical Infrastructures lab of Enea. And in the presentation that I will show you, I will talk about research activity related to the seismic analysis carried out by simulating earthquakes in a specific area of southern Italy, in order to assess the vulnerability and the seismic risk of a water distribution network located in the area close to Salerno and in the municipality of Castel San Giorgio. And we will show you some preliminary results obtained thanks to the development of a specific application which is able to simulate seismic events related to critical infrastructures. So the first issue to be discussed is the protection of critical infrastructures, because considering the occurrence of natural disasters in the world in general, and in particular in Italy, we can observe that natural disasters are able to produce huge damages in terms of deaths, of course, but also in terms of damages and failures to the critical infrastructures. Can you see my presentation? It's okay?
Yes.
Okay. Can I continue without any problem? So, okay.
Yeah.
So the critical infrastructure protection is an issue that should be handled from the technological point of view by the development of tools and approaches able to deal with this problem, but also by supporting the public administration and also the CI operators to improve their capability to deal with natural disasters and to set up prevention actions in order to protect the infrastructure, and also in order to avoid consequences to other related connected infrastructures. For example, there are specific dependencies between the electric network and the telco network. Is a typical example of interdependence between such a kind of CIs, and also moreover to prevent impacts and consequences on the population in terms of quality of services to be provided to them. In particular, we have carried out a research activity in order to analyze the impacts of earthquakes on a water distribution network located in Castel San Giorgio in the Campania region by means of an interactive simulation model, which was on purpose developed to simulate seismic events and to evaluate the potential damages by producing specific scenarios. So, considering all the possible natural disasters, we focused on earthquakes. The activities that I'm describing in this presentation are currently carried out in the framework of the Raphael project, which is a project funded by the Italian Ministry of Research. And in this project, in particular, Enea has the responsibility to develop a decision support platform called Sipcast, which aims to provide a unique framework, a unique GIS-based framework based on a huge geospatial database, able to collect data from various sources, to perform spatial analysis, and to analyze the vulnerability and the potential risks of critical infrastructures in case of natural hazard, with a specific focus on earthquakes and on floods and landslides. In this presentation, as I said, we focused on earthquakes. In particular, the results of the Raphael project will be, at the end of the project, will be carried out, will have a follow-up by means of the ASAC.IT program, which is a joint program between Enea and INGV, the Italian National Institute of Geophysics and Volcanology, in order to transform the Sipcast platform in an operational tool to be provided to the public administration and also to the CI operators. The Cpcast platform, as I said, allows to manage a large amount of geospatial data, specifically related to the critical infrastructures. And in particular, there is a module, Cpcast ES, where ES stands for Earthquake Simulator, which has been implemented to perform earthquake simulations and risk analysis, starting from a specific set of geospatial data related to the characteristics of the area of interest in terms of hazard, of exposure of the assets, the structures and the infrastructures located in the area of interest, and considering also the vulnerability of each element or each part of the infrastructure to be analyzed. At the end of the simulation process, Cpcast ES allows to obtain a damage scenario specifically related to the infrastructure considered. So we can have a scenario suitable for buildings, or a scenario suitable for a water distribution network or for electric network. In this case, the example that I will show you is a seismic scenario related to a water distribution network. And in particular, the Castel San Giorgio network is located in an area of southern Italy, in the Campania region, which is characterized by high seismic hazard, as we know, as is well known. This network is part of a test site implemented in the activities of the Raphael project that I mentioned a few slides ago. Considering the methodology adopted, we first of all implemented a workflow in the Cpcast ES application, which can be represented in the following steps. First of all, the classification of the infrastructure elements, so that in the geodatabase of Cpcast we have the description of the characteristics of the infrastructures in terms of materials, diameter size, and so on. Then the second step is to set up the simulation by input the parameters in the application. And so the parameters are for an earthquake, of course, are the epicenter, the magnitude, and the ground motion prediction equation, which is able to describe the propagation of, for example, of the acceleration or of the velocity caused by the earthquake on the ground. The next step is the hazard assessment. So such ground motion intensity measures that I mentioned before were evaluated and mapped. Then, according an approach that I will describe in the next slide, is assessed the repair rate as a function of the hazard. From the repair rate, it is possible to evaluate a sort of probability of failure, which is related to the hazard and to the ground motion, but also to the pipe length. And finally, it is possible to evaluate the damage in order to assign a specific level or a specific rate to each single pipe track. And this final result is mapped on the WebGIS interface of our application. Considering the input parameters, so we first of all selected a GMPA, ground motion prediction equation, and in particular, considering the specific case of a water distribution network, which is an infrastructure with varied pipes, it is better to evaluate the peak ground velocity, as is largely used in literature for such a kind of assets. So, in this case, the input parameters are the coordinates of the epicenter, the hypocentral depth, the magnitude, and the GMP, which allows to evaluate the PGV. Then, for really actual occurred events were selected using the parametric catalog of Italian earthquakes provided by IMGV, and we selected 4 relevant earthquakes in terms of proximity to the infrastructure, which is located in this area with the very tiny blue lines. And in particular, we selected 4 earthquakes which can be considered relevant for our purposes. Such earthquakes are used to gather the parameters to be used as input for our simulations. As I said before, another metric useful in this case is the repair rate, which is the number of leaks or of breaks per pipe length. So the seismic damage to a varied pipe can be expressed by means of such metric, where the repair rate is basically a function of the pipe material, the joint type, the soil condition, and the emitter size. And there are specific tables. You can find all the references in the web link below. And in the ALA, American Lifelines Alliance guidelines, it is possible to assign a suitable value to the K1 coefficient considering the above mentioned parameters. Then another parameter, another element of the equation which expresses the repair rate, of course, is the peak ground velocity, the PGV, which takes into account the waves propagation simulated according the seismic parameters used in the simulation, epicenter, magnitude, and so on. Starting from the repair rate, it is possible to evaluate the failure probability according to the following equation. And finally, we adopted the approach proposed among other authors, but in particular by Choi et al., which is able to provide a useful simplified classification according to 3 different levels of damage: no damage, leakage, and breakage. Of course, we are talking about probability. It is not a deterministic approach. So we can have a probability of breakage or leakage which is to be considered as a possible result of our simulation. And in the next 2 slides, I will show you 2 examples of results in terms of the scenario produced at the end of the simulation. You can see in this picture the layout and the interface of the Symmetric application. So as you can see, is a typical WebGIS interface, a typical WebGIS layout, in which we have also a specific tool and wizard which allows to set up the simulation and run the simulation. The client is a normal browser. You can access, of course, it is an access granted only to the project partners, and it is not a public access to our application. But by using a normal browser such as Chrome, Firefox, whatever you want, you can access to the data. You can set up the simulation, and you can run the simulation, which runs on server side. So the computational phase is only on the server side, and it is not on the client side, so that the user can perform the simulation without exploiting any capability of his laptop, personal computer, and so on. So this application is conceived to have a very light user interface, also from the computational point of view. And the result is an example of the simulation of the earthquake of 1980 of Irpinia Basilicata, a huge and disastrous earthquake which caused many damages in the area between Campania and Basilicata regions. And we can see a simulated scenario in terms of probability of failure, overlapped to the simulated shake map, which express the peak ground acceleration in consequence of the simulation. And this is the same example in which are reported the damages expressed in terms of levels, no damage, leakage, or breakage. And as you can see, thanks to the typical and simple WebGIS capabilities, it is possible to overlay several others GIS layers and to perform query and so on. Considering the conclusion, this tool, the earthquake simulator Viscoelastic allows to perform seismic simulation and so to perform risk analysis and to produce different damage scenarios. One of the advantages is that you can repeat several simulations by considering different earthquakes, gathering the parameters, for example, from the parametric catalog of earthquake events produced by INGV, but you can also create synthetic earthquakes considering the seismogenetic characteristics of the area in which is located your infrastructure. So it is a tool able to carry out the so-called stress tests on an infrastructure. In this case, we focused on the Castel San Giorgio water distribution network, and we analyzed the impacts of 4 actual occurred earthquakes in the area. The outputs of the simulation model that I have shown you before can represent the inputs of hydraulic simulations. So we can transfer the results via GIS format, via GIS protocols, for example, to other applications in order to simulate the hydraulic behavior of the damage network. And in this case, the next step is to evaluate and analyze post-event actions for the system recovery after an earthquake event. So this is the second part of the risk chain analysis, which of course I will not describe in this presentation. As a future developments, of course, the workflow that I described in this presentation will be further improved by considering other similar approaches developed in other studies, for example, for varied pipelines for gas distribution and transmission, which can have a different behavior in case of earthquake. And considering the calibration and the reliability of the result produced, we will perform other tests and simulations, for example, taking into account the seismic sequence occurred in the central Italy between the 2016 and 2017, started from the earthquake of Amatrice in the August of 2016. The results, in this case, will be compared, the results of the simulations will be compared with the actual post-earthquake damage surveys that have been carried out in those areas. This is all from my side. Thank you for your attention, and if you have any questions, please. Thank you again for your attention.
Thank you, Professor Pollino. Very interesting work, and I don't know if there are some questions. Someone wants to raise a question to this work from the classroom. Okay, I have a question.
Please.
So, yes, you said that as a risk analysis, it's not a deterministic methodology, but it's a stochastic methodology, and not by chance we have assigned a probability of failure for the different scenarios that is very, I think that is very similar to a Monte Carlo simulation, no? If I see the different percentage that have been assigned to the value. Would you think that so for this kind of problem, because it's like a Gaussian distribution, so this is the trend that we can find for this kind of problem, or could it be useful to consider also other kind of probability distribution for this kind of problems?
Yes, thank you for the question, because it's very focused on a crucial aspect of such a kind of analysis. I think that we have to consider other kinds of probabilistic approach, of probabilistic modeling of our approach, because in this case the approach was very simplified, only 4 events with yes, more or less a probabilistic law, but related to general purposes approaches. So what you suggest is, I mean, it should be one of our goals for the future developments. And it is also, we can also relate your suggestion with the possibility to carry out simulations with hundreds of synthetic events, earthquake events, in the same area. You can imagine a portion of territory where we can have hundreds of possible location of epicenter. So we can also run hundreds of simulations by moving the location of the epicenter along the fault, along the area interested by the fault. And so we can have a huge amount of simulation of results of parameters. In this case, a well-defined probabilistic approach is necessary to obtain reliable results and to improve the value of our simulation. So yes, and your second suggestion is well centered on
in order to see how the results can vary with different distribution. Okay, thank you, Professor. Thank you.
Thank you again. Thank you again.
If there are other questions, I don't know. Okay, perfect. We can go on with the next presentation. The work is Security and Resilience in Small Centers of Island Areas. Work was carried out by Priscilla Sofia D'Astoli, I think, and Pier Giuseppe Contrandolfi. And the work will be presented by Priscilla Sofia D'Astoli, no?
Sì,
okay.
Sì, esatto.
Perfect. So, the ground is yours.
Thank you. Okay. Do you...
Yeah, we see.
Okay, I'll start. Our contribution starts from the consideration that after the pandemic emergency could be credible a gradual rebalancing of the relationship between urbanized areas such as cities and metropolitan areas and inland areas such as small towns or rural areas. In this perspective, it's important to consider the risk level present in inland areas, natural and human risk, and how to provide specific interventions of mitigation, and how to increase through the growth of the territorial security level the resilience of these territories. The research is developed through approaches of a gradual approach to the main topic, with a study that consists of 3 parts. A strategy to increase the resilience of the territory, a seismic risk mitigation in built-up areas, and the recovery strategies of the existing building stock. In other words, we experiment with the integration of the so-called emergency limit condition CLE and minimum urban structure, as defined in national and regional legislation and in the scientific literature of the sector. The structure of the research consists of five phases. The analysis of the limit condition of the emergency, identifying the strategic elements of minimum urban structure, the evaluation of CLE considering the elements of the sum, the development of a urban system for seismic emergency management, and finally, the recovery of critical construction that interfere with the emergency management system, because not everything can be done, but priorities must be identified. To introduce a new methodological approach for emergency management, it's essential to implement a phase of knowledge of the housing fabric, because each inhabited area is unique and therefore reacts subjectively to adverse events, such as an earthquake. Our experiment took place in a small mountain municipality in the Basilicata region, located on a promontory. The mitigation of the seismic risk on an urban scale is commonly associated with the analysis of the limit condition for emergency, so-called CLEM, which identify places of coordination, emergency areas, and connecting infrastructures, in which the rescue system must be articulated following of an earthquake. The CLE analysis identify buildings that are blue in the map, and the areas yellow and red in the map, and the infrastructure for the emergency that are linear elements. Furthermore, the aggregates that interfere with this system are reported on orange in the map. In the municipality of Moliterno, it can be observed that the elements of the CLE are external to the fabric of the town, especially outside the historical center, and therefore the recovery of the settlement after the earthquake may be compromised. The study on the minimum urban structure, on the other hand, represents the modality through which system of route, spaces, and strategic buildings are organized in advance for the response of the settlement to the earthquake. But in order to allow a rapid resumption of ordinary urban activities after the occurrence of the event. The innovative contribution is related to a possible integration between CLE and SAM, in particular considering not only the elements of the emergency phase, but also the strategic components for the resumption of the settlement after the earthquake. These strategic components are such as economic activities, places of relationship, and above all, historical centers. As can be seen in the diagram, it's necessary to pass from an extremely emergency configuration outside the built-up area to an internal one, functional to recovery. The ineffectiveness of the claim for the municipality of Moliterno emerged from a specific evaluation considering the comprehensiveness criterion, the efficiency criterion, and the urban compatibility criterion, and it was noted that the strategic function of the settlement are not considered in this system. So the new CLE configuration given by us is reported for the municipality of Moliterno, which in this way have improved its urban response to the earthquake because there are major strategic function for recovery, and also we include the historic center in the system. Infrastructure leading to strategic function can be compromised due to localized collapse. In fact, all the buildings interfering with the emergency management system have been identified in yellow. Buildings represent a critical issue when they are higher than the road section. A study on the interfering and critical elements was done, considering aspects such as the state of conservation of the buildings, the building consistency, the construction type, and the degree of use. For these buildings, seismic adaptation and improvement intervention must be implemented. The recovery must not be an end in itself, but for recovery properties, the intent in the use must be linked to the priority function, such as tourist accommodation or hospitality, and widespread residence for the elderly, but also for management center and associated services. We conclude by saying that if we focus on minor historical center, it's possible to identify destinations of use capable of contributing to development of the area, because they represent an heritage of cultural identity that cannot be neglected. Priorities must be identified in each settlement so that the individual intervention can act both to reduce seismic risk and to create new housing. The current pandemic crisis must lead to a profound rethinking of the development model and a change in policies for city and internal territories to ensure sustainable development that it establishes itself as the only possible choice. Thank you for the attention.
So thank you to Professor Dassoli for this presentation. Very interesting and important for the current, I think, I was thinking about Valori Paese di More, that is a project of some years ago for the minor centers. No? So very important now to take into account a focus, so to put the spotlight on these areas. Okay, so if there is someone for possible questions.
I have just a question for you. First of all, it was really an interesting presentation, an interesting work, and just a question about the seismic risk for the interfering buildings. How do we evaluate the seismic risk for this building in an extensive way, or by considering specific vulnerability and risk for each building? is an extensive approach or a single building approach?
No, we don't make a study of this type, but we start from the consideration that some areas important for the settlement can be excluded from the system management of emergency.
Okay.
So we include infrastructure that pass away from the historical center of or the area of relationship in the settlement, and include give the possibility to act in this area, and for the recovery of the buildings.
Okay.
We make a study only on the state of conservation or the height of these buildings.
Okay, thank you. So, for example, a seismic simulator can be useful. So we can, as a future common development of our activity from both our sides could be this one. There is a point of contact because we can support you for the seismic simulation. You can support us for the CLA analysis, for example. So this is a sort of idea of development.
Okay, thank you for the question.
Thank you again.
Okay, we have a question from Cagliari.
Good morning. I was just wondering if the evaluation of the seismic risk and the planning of the seismic hazard has been a part of a general plan, or it is just something that has been done after a seismic event?
Yes, thank you for the question. No, in the past there were several earthquakes that destroyed these buildings of the settlement of Moliterno and municipality near in 1857 and 1990. The earthquake that was named by Pollino before. But we make a study before this part, where we note that the area is in the classification seismic of Italy is in the first class. So it's a very an area very.
There's a high probability to repeat this kind of event.
Yes. So we make a study of a general study, but there is not a plan. But the integration between CLE and SUM that we present can be introduced in the plan of the cities of the settlement.
Sure, no, just to understand the logic that you are following.
Yes.
Thank you.
Thank you.
Bye to Maurizio and Francesco.
Ciao Francesco.
Ciao Francesco.
Ciao. Okay, can I ask also, is it possible, the last question or the last consideration about the maintenance condition? I thought that you have defined the maintenance conditions through a tour, no? A tour in the town, and you decide optimum, good. Are there also, have you thought, because this is a problem, because it's the problem could be that at the end you have a map that can be also a little subjective. Have you thought also to a table with the different factors that define optimum good? I don't know if I managed to be clear. No.
No, I'm sorry.
Sorry. When you show the map that concerns the maintenance condition,
Yes.
no, I saw different colors that represent the different level of maintenance condition.
Yes.
Okay. How have you defined these levels?
Okay, it's very simple because in this settlement of Moliterno there is the plan name Regolamento Urbanistico is the name of this plan, but it's not approved. In this plan, there are many activities of investigation of the settlement because it's not an our map, but it's a study that the group of technical
Of the municipality have developed. Okay, understood. Okay, thank you.
Okay.
Perfect. Thank you all, and I think that we are in time also with your presentation because it's 10 o'clock, 9:57. So I would like to thank all the researchers, Professor Maurizio Pollino, the other chair of this presentation, and I hope to see all of you next in the future workshop of Emewe and Aster, and I wish that you will enjoy to continue to enjoy this outstanding conference. Today we have another lecture, a very interesting presentation, Digital Health, Back to the Future, keynote lecturer of this afternoon. And okay, I don't know if Professor Pollino wants to close the session.
No, thank you for your kind words toward my presentation. But yes, I wish to see you again in presence in the next meeting, in the next occasion, and I think that this workshop would have also other possibilities to be further carried out in the next edition of ICCSA conference. So I think that now is the time to plan the future work for the next papers and contribution for the next edition of Aster. And I would like to thank you for the participation and for the attention to our workshop, both Emewe and Aster, and see you in next occasion. Thank you again.
Thank you to Dr. Sagarneti, Lucia Sagarneti, that I forgot to thank yesterday. Thank you for your work.
Thank you so much.
Okay, so it's 10 o'clock. Goodbye, everyone.
Goodbye. Thank you.
Good morning. Good morning to everybody. I'm Giuseppe Ganeti. I'm the assistant of this session.
Good morning.
Good morning. Mr. Fernando Miranda, you are?
Yes, I'm chair of this session.
Perfect. For the other participant, if you want to put your name, you can click three dots.
I already put my
Yes,
name
yes,
in
I
the,
can see
I
your
think.
name. For the other, if you want, you can put on the three dots near the red phone, and in the first line you can insert your name if you want. Now we are yet online on YouTube.
Okay.
And I think in 7 minutes we can start. Mr. Miranda, if you want to verify the presence of the other speaker, you can.
Okay. I think some of them they have not put his names. Karin is here. I'm hearing to myself.
Okay.
Tens uns 3 pontinhos. Karin, are you there? Ok. Eu acho que é o telefone aberto. Não.
Fazer a Karen, a primeira é mexer.
Eu sei, mas a única que está aqui.
And sorry, Mr. Miranda, just a little reminder for the evaluation form. I remember you to fill out for each presentation.
Okay.
If you want, I send you the link in the private chat for the evaluation form. Okay.
Okay, I received the link. How many times do I have to fill the forms?
Oh, you can fill out also after the session.
This link I can use to all the presentations?
For all the presentation, yes.
Michele Silva is not here. Michele. No. Luís Ferraz? Karina, are you there?
Karini is here.
Okay, thank you. Are you in Brazil? Karina? Yes. So you should be sleeping now. Fala português, Karina?
Sim, falo.
Ok. Que horas são aí, Karina?
5h15 da manhã.
Uma boa hora para estar a dormir, não é?
A diferença do fuso horário são 5 horas.
Pois é, muito tempo. Ok. Vamos esperar. Ainda não tenho. First speaker is not here yet. Someone is coming. Michele Silva. Luís Ferraz já chegou. Olá, Luís.
Olá, hi.
Hi, how are you? We are waiting for the first speaker. Lucia?
Yes. We can start.
Yes, we can start, but the first speaker is not here. How do? I wait for the second talk?
Yes. You can start with the second speaker.
I can start with the second speaker?
Yes.
Okay. Luís? The first speaker is not yet here, so probably I will ask you if you can start your talk now. Can I change and you pass to be the first speaker, Luís? No sound. Turn on sound.
Okay. I'm the first or the third?
No, you
speaker?
are second, but the first speaker is not here. So I asked to the
Okay.
Probably I don't know if he is late. I don't know. He's from Brazil, so probably he's sleeping yet.
Okay. I will just.
Okay. Yes. So let us start. I would like to welcome all the participants of this session, Computation and Applied Mathematics. I don't know. No, I don't think so. So I recall that each speaker has 10 minutes for presentation, okay, and 5 minutes to discussions and questions. So the first speaker is Luís Ferraz from Portugal, University of Minho, and he will talk about a numerical method for the transient wet flow of a distributed order viscoelastic fluid. Please, Luis.
Okay, Professor Fernando, thank you for the introduction. Good morning to everyone. Can you
Morning.
all see my presentation?
Yes,
can you
yes,
hear
it's
me?
perfect. Okay.
Okay. As Professor Fernando said, the title is a numerical method for the transient wet flow of a distributed order viscoelastic model, and this is a joint work with Professors Luisa Morgado and Professor Magda Rebelo from IST, University of Lisbon, and New University of Lisbon. So I'll start with the motivation and objectives. Then I'll pass on to the viscoelasticity and present some basics about viscoelasticity. I'll present the model that we are interested in and we want to present in this presentation. Then I'll finish with a numerical method and conclusions. So basically the motivation and objectives of this work are to develop new models that can predict the behavior of complex materials such as saliva, blood, plastic melt, or polymer melt. And since these models are quite complex, we would like to derive a computational model, a numerical method to better understand the behavior of such model. So I'll present a brief introduction to classical models and then fractional models before introducing the new distributed order viscoelastic models. So a classical model for viscoelasticity, as you can see in the name, we have visco and elasticity. Visco comes from viscosity and elasticity from something elastic. And this is due to the combination of a spring and a dashpot. The spring represents the Euclidean elastic solid, and we can see here our hand stretching the string. And as we stretch this string, we will feel here some force or stress. And this stress is proportional to the deformation, which is this gamma here of elastic deformation. So the more I try to pull this string, the more I feel the stress in my hands. And for a dashpot, the result is not quite the same. And in this case, what happens is that the stress I feel here in my hands is not proportional to the deformation, but now it's to the rate of deformation. So the velocity I impose when I try to stretch this. If I combine these two elements, the spring and the dashpot, I obtain what is called a Maxwell model. And this is a differential constitutive equation. And in order to understand how this model behaves, I have here an example where you can see that in this case, I have a spring and a dashpot, and I'm not trying to stretch, so I don't feel any stress. At instant A, I stretch these elements, and then I stop. And you can see that I start feeling the stress in my hands. And then as the time goes by, here is the graph of the stress. The stress starts to decrease, but the distance is the same. What happens is that the dashpot tries to compensate for this elastic behavior here. So the Maxwell model is given in this differential constitutive form, but it can also be written, if we integrate both sides of the equation, it can also be written in an integral form, which is shown here, but I just want you to look at the first term. Stress is equal to this integral that goes from 0 to the actual instant. And we have here a negative exponential, which is a kernel, and we have a derivative of deformation. So along the time, several models were proposed in the literature because Maxwell model may be good to model one part of a material, but imagine that I have a portion of material, but I'm not expecting that in the different regions of the material, I have the same molecular arrangement. For example, in this region, I have these straight lines. These are the molecules. And in this case here, I have entanglements. So it means that my viscoelasticity won't be the same here and here. So a solution that was proposed in the literature was the use of not one, but several constitutive models with different parameters in each model. So more recently, new models start being used that are called fractional viscoelastic models. And basically they are based in fractional derivatives. And so fractional derivatives are derivatives that do not need to be of integer order. For example, I can have a derivative of order 0.1 or 0.3. These derivatives are successful because Imagine that I have some physical phenomena that is being developed at a certain rate. And if we use the classical derivatives, we can only study rates of 1, order 0, order 2. And of course, physics doesn't know that, so we may have phenomena that happens at rates of 0.1, 0.2. So to understand how these fractional derivatives work, let's just take a look at the fundamental theorem of classical calculus, where we have this capital F here, which is written at this integral of this f function. And we all know that if we apply the derivative in both sides of this equation, we obtain that the derivative of f equals the integrand function. Now let's define the n-fold integral and the n-fold derivative. By n-fold, I mean the integral of the integral of the integral n times, and n-fold derivative, it's the derivative of the derivative of the derivative. So we would expect that to represent this n-fold integral, we would need to use n times the symbol of the integral. But this is not the case, because we have a lemma that says that the n-fold integral can be written with just one symbol of integration, but now we have this n-1 factorial here, which is highlighted because it answers the question, how can I generalize this integral to non-integer values? This is the integral, not derivative, but the question is, how can I generalize this? So here I have no problem, but in this case I have problem because this is a factorial and I cannot generalize it. So one way to generalize this is to use the Gamma-Euler function, which generalizes the factorial. So up to now, we can obtain generalized integrals, but we don't have any generalized derivative. So the solution proposed in the literature is to use these integrals to create our derivatives. So since we have no restrictions in this alpha here, which may be a real value, what we do is to apply the mth order derivative to this m minus alpha integral, and we obtain our alpha derivative, or we apply the integral to this derivative of the integrand function. These are two similar definitions of fractional derivative, but they are quite different in what respect to final results. So this is called the Riemann-Liouville derivative, and this one is the Caputo derivative. So basically, these fractional derivatives, they have they use integrals. So now, what does this has to be with viscoelasticity? So sometimes some materials present different relaxations than the negative exponential, and then show this exponential decay. And if we substitute this exponential decay with this form in our model that I showed you before for the Maxwell model, we obtain this expression. And if we compare this expression with the definition of the Caputo derivative that I just showed you before, we can see that it's quite similar, which is basically the same. We just have this extra constant, which is a constant related to the model. And we have here the derivative. So we can generalize these fractional models to these fractional derivatives by just using this kind of kernels. And here you can see the model in a compact form, and this represents the Caputo derivative. A possible mechanical representation of this derivative, this fractional derivative, is given here, where we have this ladder structure with different parameters, and of course, since we have so many parameters that are embedded in a model, we're expecting to obtain better results. This figure is just to show a possible combination of these models. In this work, we are interested in more complex model, which is basically what I'm going to tell now. Here I have the fractional derivative, the classical fractional derivative that I showed you before. And the distributive derivative, what it does is to perform a continuous sum over the alpha parameter of the orders of the derivative that goes from 0 to 1. So basically what I'm doing here, I'm summing up a weighted fractional derivatives, and the alpha values just go from 0 to 1. So a way to derive the model based on this derivative is to assume that the kernel is given by a sum of different algebraic decays. If we assume that this n value goes to infinity, basically we obtain this expression here, which is if we substitute this in our classical model that I showed you before, we obtain this distributed order derivative. This d represents the derivative that I showed you before. So since this is a really complex model that has two integrals and derivatives, we cannot obtain an analytical solution, so we implemented a numerical method. And to better understand this method, we consider a really simple flow, which is this 1D transient quad flow, where we have a lower wall and an upper wall, and I have a small portion of fluid between these walls. And the upper wall starts to move with a certain velocity. The equations governing this flow are these ones here, and this one here. This one is for the velocity, and this one is for the stress. But you can see that they are connected because I have stress. This is a shear stress. That's why I use xy. And I have also velocity in this equation here. Note that this kernel is given by an integral. So if I expand this equation here and I substitute this on the first one, I obtain this equation for the velocity where I have derivatives, integrals, another derivative, and evolution in time. So this is a expanded version of the equations that I showed you before. So this first equation only depends on velocity, and this one depends also on velocity. But here we have the stress. So the idea to solve this problem is to first discretize this equation, obtain the velocity, substitute in the second equation, and then obtain the results. These are the initial conditions. This means that the bottom wall is fixed and the top wall is moving with a certain velocity phi. These are the initial conditions, which is the velocity is 0 and the derivative. And the stress is 0, meaning that the fluid is relaxed. So I will divide this integral that goes from 0 to a certain time into smaller integrals. Here I have no approximation. And then I will perform an approximation. I will use the midpoint rule to take this term out of the integral, and I will approximate the second order derivative with a second order finite difference approximation. This term here is obtained analytically. I also use the midpoint rule to approximate the integral that goes from 0 to 1, and I use a finite difference approximation for the evolution in time, first order. So here is the discretized velocity equation, and after solving this equation, I obtain the velocity that I can substitute for the stress and obtain the stress profile. We just have some preliminary results. So we fabricated a solution which is non-smooth, as you can see here. So we have a singularity at the origin, and we just measure the error. We tried the different meshes because the solution of this problem takes some time. And we consider more refined mesh and a less refined mesh. And in both cases, we obtain small errors. So we opt to use the less refined mesh to perform the following tests that I showed you, that I will show you next. Here you can see a comparison between the analytical solution and the numerical solution. So the physical process that I talking to you about before, I have an upper wall, lower wall, and here I have a portion of fluid. I will just move this wall during 50 milliseconds, and this is the velocity of the upper wall. It mimics a Dirac delta function. And so what I want to see is that I move, I stop, and I want to see how the stress relaxes. Here are some results with different weighting functions, and you can see that exactly when I move the wall, I have a peak because the stress or the elastic part is reacting to this movement, and then the stress starts to relax. These different functions here attribute different weights to a more liquid, more solid behavior when this alpha is 0, and a more liquid behavior when alpha is 1. And you can see that the peak increases when I have a more liquid behavior. So the conclusions, we developed a new numerical method. This method can be used to understand the distributed order viscoelastic model. But in the future, we will need to perform more tests and to try to understand better the model considering different flows. So thank you very much for your attention. I think I took the 15 minutes. Sorry.
Yes, we are out of time, but we have...
Sorry.
No, no problem. We have time for a question, a small question. Any questions?
Yes.
Yes, please.
Yes, of course.
Just to have an idea, because you have used during your method several numerical methods, second order numerical methods for computing the integral and the differences, the finite differences. Do you have a theoretical result showing the order of convergence of your method, or it's just still numerical experiments?
Yes, for this case, I only have the theoretical results for solvability. For convergence, no, I don't have theoretical results, but I have experimental results. We tested, but it was yesterday. So, but the order of the method is not very good. It's approximately 1, and in these cases, when we have this alpha parameter, it usually depends on the alpha, so it's a quite low order of convergence. So we need to improve this in the future.
Okay, thank you.
Thank you.
Thank you, Luis. I think the first speaker is not arrived yet. Michele Silva, are you there? No. So probably I will ask to Karine Zampiroli if you can be the next speaker.
Yes.
Yes, thank you very much. So can you share the screen?
Sorry, I ask for the first participant to stop the sharing screen.
Okay, Luis? Luis?
I'm sorry.
Okay. Okay, maybe full screen, yes. Perfect, ok. Oh, no. Ok. Yes.
Deixa eu ver se meu fone tá ligado.
Tá.
Yes.
So,
you see my presentation?
Yes, it's perfect. The second speaker is Karine Zampiroli from Brazil. So it is very early, but he will talk about hi, and Karine will talk about simulated annealing and the iterated local search approach to the aircraft refueling problem. Thank you, Karine, and you can start.
Yeah. Hi, I'm Karine, and I'm going to present the work, the simulated annealing and iterated local search approach to the aircraft refueling problem. To prepare an aircraft for takeoff, the airport offers road services such as service, baggage, cleaning, toilet, loading, catering supplies, and refueling. A good schedule in the refueling operation avoids delays in the takeoff aircraft. The aim of this work is to study the aircraft refueling problem, ARP, using tank trucks. There is little research that studied the refueling aircraft. Babbage was the first author that presented a model for aircraft refueling. In his study, minimized the number of refilling trucks and minimized the truck's total travel distance. The author Du et al., Wang et al., and Ramaywanti et al. Studied the ARP. This ARP is adapted from a vehicle routing problem with time windows to incorporation hill characteristics. In ARP, there are a set of aircraft and non-homogeneous tank trucks. Each aircraft I requests a quantity of fuel Ci, and refilling activity begins during predetermined period of time AI and BI. The aircraft I is served using a single truck. Each truck has capacity maximum, and each truck starts at the depot, serves some aircraft, and returns to the depot. To construct the route, it is not mandatory that aircraft I is served before aircraft I plus 1. Aircraft I located in straight line. We consider the refilling rate of an aircraft to calculate the service time and the average velocity of the truck to travel from one aircraft to another. We describe a mixed integer linear programming MILP model. The aim of ARP is to find the short distance traveled by tank trucks to meet fuel demands requested by aircraft at an airport. That is, we want to find the minimal cost routes, one for each truck, where each aircraft will be visited only once. This simulated annealing as a and iterated local sort iOS algorithms were implemented to solve the problem. The SA method considers an initial solution S and temperature as a max iteration are performed and an initial solution is found by performing local sorts in the neighborhoods of the current solution. The iOS that consists of exploring the search space through disturbs in best location. iOS starts with the initial solution and applies a local search. Then perturbs the current solution and performs a local search, reaching a local optimum. To determine a feasible initial solution for algorithms, two methods were defined. Random construct heuristic RC8 and nearest neighbor heuristic NN8. Savage for renting movies type were used to make changes to solutions such as shift, swap, and recession moves. The evaluation function selects solutions that meet a certain acceptance criterion. The local search method generates, at each iteration, solutions that are neighbor of the current solution and accept only solutions that are better than the current. The data used for experiment correspond to the premise observed at the Heathrow Airport. We construct a set of 8 instances with 6 to 4 aircraft and 6 to 10 available trucks. Instance number of aircraft 6 to 4 and number of available trucks 6 to 10. The Numerical model was served using Simplex and maximum execution time of 2 hours. SA and iOS algorithms were coded in Python. The parameters of the SA and iOS algorithms were determined by experimentation. The heuristic what obtained better results was an N8 heuristic to construct the initial solution. 6 variants of the algorithms were implemented using the local search with a random neighborhood consider different moves. There were 3 variants of the SA and 3 variants of the iOS. In the table, we have the solution for Simplex and 6 variants of the 8 instances. Looking at the values in bold, we can consider that the 4th variant produced the large number of best solutions in the 8 instances. The variant 4th corresponds to the execution of the iOS using the local search with an inter-root neighborhood structures considering only 4 moves. Passei uma mais. The ARP is NP-head. It is expected that the exact approach will not be able to efficiently solve large instances. Simplex proved the solution optimally only for instance 1 and 2. For instance 7 and 8, up to 40 aircraft, Simplex did not find an optimal solution after running for 2 hours. The iOS heuristic provides good results at a favorable time when compared with the 2 hours of Simplex execution for instance 5, 7, and 8. Conclusions. We designed a Numerical model and SA and iOS algorithms for solve the ARP. We tested the variant of method for generate initial solution and generate neighborhoods. The computational experiment showed that the iOS is an effective approach to solve the problem, and the Simplex could solve only small instances. In future research strategies to improve the efficiency of the present algorithms are to be considered, and strategies to address instances that involve extreme infeasible cases. Thank you very much.
Okay, thank you, Karine, for your presentation. So we have time to questions or comments. May I ask you one thing? Each truck can refuel more than one aircraft or not?
Sorry, I don't understand. Can you please repeat the question?
Yes, my question is, each truck can refuel more than one aeroplane or not?
Aeroplane.
Aircrafts, yes.
Yes.
The answer is yes?
Yes.
Okay, another thing, did you have test these algorithms in any real situation, or the experiments are only simulations, probably in the computer?
Sorry, I don't speak English very well.
May I ask you in Portuguese, probably? I think I don't know, but do you understand the question, and you answer in Portuguese or in English, if you want. A minha pergunta, Karine, foi se estes algoritmos foram testados em alguma situação real ou foram apenas simulações feitas provavelmente em computador.
Essas instâncias aqui criadas foram instâncias baseadas em premissas reais, certo? Foram premissas observadas em um aeroporto real. A partir dessas instâncias construídas, então, nós trabalhamos com duas abordagens de solução, que foi o algoritmo Simulated Annealing and Iterator Local Search. Desses dois algoritmos de solução, nós criamos 6 variações por meio de alterando as buscas locais. E aí, baseado nessas instâncias reais, nós executamos no Cplex e nos algoritmos Simulated Annealing and ILS. Obtemos esses resultados aqui. Com as 8 instâncias criadas, nós temos os valores das distâncias, né, que são rotas construídas. Então, na instância 1, nós temos essa distância obtida pelo Cplex e aqui, consequentemente, obtido com as 6 variações. Então, nós podemos observar que a 4ª variação, que é exatamente o algoritmo Iterator Local Search, ele obteve melhores resultados, ou seja, menores distâncias, né? Inclusive comparado com os tempos de execução, que aqui a gente pode observar nessa tabela. Então, as propostas de soluções foram por meio do Cplex e de 2 algoritmos. Só que quando a gente trabalha com uma complexidade maior, isto é, quando as nossas instâncias elas são maiores, o Cplex, né, que obtém uma solução exata, ele não tem capacidade de resolver, né? Ele extrapola o tempo, né, de 2 horas, ele extrapola o tempo e não obtém uma solução. Então, nós temos, então, as propostas dos algoritmos, né? E aí, a gente consegue encontrar rota para que resolva as instâncias construídas.
Okay, thank you very much. Any other question or comment? No? So, thank you, Karine. I will repeat the question. Are you there, Michelle e Silva? No? So, let's present the next talk. Yes. Can you share? No. 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 should start. Control L. Okay, so next speaker is Maria Irene Falcão from Portugal, University of Minho, and she will talk about a Pascal-like triangle with quaternionic entries.
Hello, thank you. In this talk, I will focus on some properties of a special arithmetic triangle whose entries are quaternions. This is a joint work with Helmut Malonek from the University of Aveiro in Portugal. Let me say a few words about the reason behind this work. Our motivation came from the fact that, as it is well known, several combinatorial problems are successfully solved by using complex analysis method. Having in mind that hypercomplex analysis is a generalization of complex analysis of one variable to higher dimensions, it seems natural to expect that using tools from hypercomplex function theory, new combinatorial problems can be solved. And recent works show that this is in fact true. So, over the years, several authors have constructed arithmetic triangles by choosing as their elements numbers which satisfy this recurrence relation, a recurrence relation of this kind with appropriate coefficients and initial conditions. These triangles, the triangle, for example, the triangle corresponding to this condition here, reduced to the well-known Pascal triangle, whereas these initial conditions here lead to the so-called Lucas triangle. A third example, with these coefficients, this is not a constant coefficient, the initial conditions are the same as in the case of the Pascal triangle, we obtain the Stirling triangle of second kind. So the idea here, or the goal of this work, is to consider the arithmetic triangle obtained by choosing as coefficients here the generators of the Hamilton quaternion algebra. The initial conditions that you are going to use are the same as in the case of the Pascal triangle. We will present several patterns in this structure and discuss its main properties. They reveal, in a very particular form, similarities with the classical properties of Pascal triangle with real entries, and at the same time illustrate the consequences of the non-commutativity of the quaternion algebra. So, as the time is running, I will just recall the essential background to follow the presentation. I will also skip all the proofs and technical aspects. You can see, if you are interested, all the details in the paper. So, we assume that we have n vectors here in Rn, forming an orthonormal basis, and we have this multiplicative rule. This is the Kronecker symbol. This non-commutative rule generates the Clifford algebra CL0n, which has dimension 2 to the power of n. These vectors here are usually called imaginary units or generators of the Clifford algebra. I have introduced the general setting because if time allows, I can talk a little bit about generalizations, but in fact, I will focus on a particular Clifford algebra. Let me just show you that in the case where n is equal to 1, we have the two-dimensional algebra generated by A1, and if you identify A1 with the complex imaginary unit, you can see that CL01 is isomorphic to the complex setting. The case n equals to 2 is the case that we are interested with. is, in this case, we obtain the 4-dimensional algebra. These are the multiplication rules. If we identify as Hamilton, this was the notation used by Hamilton, you can see that we have, in the case n equals to 2, the quaternions. So let's have a look at the triangle that we obtain with these multiplication rules and this recurrence relation. We have here A1 or I in the Hamilton's notation and A2. The initial conditions are these. If we apply the multiplication rule, we obtain this triangle here. This I'm showing you just the first 5 rows of the triangle. If you concentrate on this on the first row, if you look at the first row and the diagonal, you can see that this initial condition can be expressed in this way. So now we can consider the norm of each element of the triangle. If you consider, we end up with this triangle here, which is known in the literature as poly-Pascal triangle. This is a triangular array made of 3 copies of the Pascal triangle. It is easy to see that the entries of one of the triangles are the non-zero elements of each even row. I'm going to use orange here. You can see the Pascal triangle, and the other 2 are obtained by considering alternate elements, blue and red, of the odd rows. Another property of this triangle concerns the row sum. If you look, for the first row, we have 1. This is the sum of the second row, the third, and so on. So we can prove that in the case of the quaternionic Pascal triangle, the row sum depends, as we can expect, on the parity of k, of the rows, and is given by this form here. In the case k is even, we have a real number, and in the other case, we have a quaternionic number. Let me just recall that in the case of the classical or real Pascal triangle, the row sum equals 2 to the power of k. So now, if we consider the row alternating sum of the numbers in the even columns here in orange, we are going to forget the first 2 rows because they are not going to follow any pattern. So as I was saying, if we consider the alternating sum of these orange numbers, you can see that they equals to 0. And the same is true if you consider the odd columns. The alternating sum is true. This is in line with what we know about the real Pascal triangle, because in this case, the alternating sum is always 0 for k greater than or equal to 1. In this case, we have k greater or equal to 2. Another property, if we sum for each row the squares of the numbers, we obtain these numbers here. Let's have a look to the orange numbers. We can see these orange numbers are here. Of course, I don't have more rows because I don't have space. They are here. And we can see that the blue numbers are just twice the symmetric of the previous orange sum. The formula is this one, and in the case of the real Pascal triangle, it is well known that the row sum square is equal to the central binomial coefficients. here, if you look, if you look at the position of these numbers, you see that these numbers are in the central position of the corresponding row, exactly as in the case of the Pascal triangle. So, of course, that we can think on generalizing the idea of using the generators of the algebra for higher dimensions. What we have to do is to use this recurrence relation here. Now we are using the generators of the Clifford algebra, 2n dimensional Clifford algebra, and we can arrange these numbers in a structure, and this structure is very similar to the Pascal simplex. Of course, that I cannot show you any picture of the Pascal simplex, general Pascal simplex, but to give you an idea, I will show you briefly the case n equals to 3. In this special case, the numbers can be arranged in a tetrahedron. Now, instead of rows and columns, we cannot talk about rows and columns, but we can talk about cross sections or layers and facets, and we can have a closer look at the layers. For example, this is the first layer, just number 1. The second layer has these triangles where you can see the generators of the algebra. This is the third, and so on. If these are the layers, if you look at the facets, for example, this, you can see this here, you have the number 1, A2, A3, -1, 0, -1, -A2, and so on. So you have something like this. Let me just recall that in the real case, the real Pascal tetrahedron, the 3 facets coincide all with the Pascal triangle with real entries. You can see 1, 1, 1, 1, 2, 1, all the facets. In the case of the quaternions, this is not true. For example, if we look at this facet over here, we have this triangle. This is, in fact, the triangle that I have showed you before. The recurrence relation is here, is this, A1 and A2, but the other facets are not the same. They are similar, but instead of using as generators N1 and A2, we have to use A2 and A3, and in the other case, A3 and A1. So I would like to show you now, to finish my talk, a table where I have some of the properties that I have shown in the paper, not for the Pascal simplex, but for the Pascal triangle, hypercomplex Pascal triangle. We can see here the recurrence relation. This is an explicit expression of the coefficients. Here is the row sum, the alternating row sum, and here is some nice combinatorial property that I do not have time to talk about, but in fact, what we have observed is that during our work, we found several nice combinatorial properties, far from our research interest, but even so, we think that they are very nice. So I have shown you only the results that can be easily illustrated. The paper contains other results and combinatorial relation that can be useful for development of new techniques when working, for example, with polynomials in higher dimension. Thank you very much for your attention.
Thank you, Irene, for your dynamic and colored presentation. Very beautiful. Any questions or comments?
I have just one
Yes, Luis.
last question. Can I ask?
Yes, please.
Professor, a very nice presentation. Congratulations. Just a simple question. For example, when you have that hypercomplex triangles, and you told us that you could obtain some relationships, were that relationships obtained from the formulas, the combinatorial formulas, or you could take a look, for example, n equals to 4, and you start drawing the numbers, and you could find any relationship?
Thank you, Luis. In fact, there are several ways of proving the kind of relation that I have shown you. In this work, we decided to start with the recurrence relation. And with the recurrence relation, we can find a general expression and then prove everything. I have just shown you the results that I thought it was more interesting to show in the presentation. But in fact, they are proved in the paper using all the starting point is the recurrence relation. There are other ways to prove this kind of properties, but this is what we have done.
Okay, thank you very much.
Okay, thank you. Any other question? May I probably do a question? Is there a binomial formula to this situation?
Yes, there is a binomial formula. The only thing that is different from the the classical case is that we cannot use the usual powers. We have to use what we call the symmetric powers, which are related to a different kind of multiplications. In the multiplication case, for quaternions, the multiplication is not commutative, but in several results in quaternion analysis, we have the need to introduce another kind of product, the so-called symmetric product. This symmetric product, as the name says, is commutative, but not associative. And so, but by using this kind of product, it is possible, and it is done in the paper, it is possible to obtain a binomial formula similar to what we call the Newton's binomial.
Okay, thank you. I will ask, I will try to contact Michele Silva. It's the last opportunity. No, it is not here. So let me thank all the speakers. Now we have a coffee break or some kind of coffee breaks. And we start at 11:30 local time. Okay, see you.
Thank you.
Thank you. Falaste. Agora estão, por exemplo, 18. Mas falaste, pai, 13, 14 minutos. Não. Até uma altura ia-te dizer para acelerar um bocado. Mas depois percebi que tinhas pouca coisa. Não?
Sim, mas eu meti assim algumas coisas que não estavam lá.
Ok, agora não queria nada falar.
Hã?
Não apetecia nada falar disto.
Vamos tomar um cafezinho. Eu já estou livre. Notou-se que estava a ler?
Não, não.
O que é que vais fazer? O que é que tens de
Não, dá para pôr aqui.
Afinal, não se ouve. Eu posso falar e não se ouve.
Não disseste para desligar o mic.
Disse, mas acho que para não desligarmos.
Is on. Is on.
Good morning. Can you hear me?
Yes. Good morning.
Okay. Excuse me, can I try to make a proof of the presentation?
Sorry? Yes.
Thank you. Is it working?
Yes, yes.
Thank you.
Perfect.
Miss Maria Irene Falcao, sorry for the pronunciation. If you want, we can start in 4 minutes.
Okay, okay.
Okay, thank you.
Thank you.
Irene, não queres contar-se alguém nessa sala?
Probably we can check if all the speakers are present. I think that the first one is Fernando Miranda.
I'm here.
The second one is Valdivino Santiago Jr.
I'm not Valdivino, I'm Gabriel Pazza.
Gabriel,
the co-author.
okay. Because we did not have the information about the speakers. We know all the authors, but the speakers no. Then Fernanda Costa, I think it's going to be here. Then I think it's not Daniela Santilli, but Azure Evangelisti.
Exactly, yes.
Okay.
Thank you.
Then Juan Gonzalez. No? Juan Gonzalez, I'm sorry. Juan Gonzalez in the afternoon. So I think that everyone is here. Fernando, would you like to share? So I think that now we can start. I would like to welcome you to the second part of the session, Computational Applied Mathematics. Our first speaker is Fernando Miranda from the University of Minho. He's going to talk about mathematical tools for co-quaternions. You can start if you want, please.
Thank
Sorry, the microphone.
I'm sorry? No, can you hear me?
Yes, okay.
Thank you very much, and I'm sorry. So, in this talk, I will present a computational toolbox created in Mathematica to work with the coquaternions. This is a joint work with Maria Irene Falcão, Ricardo Severino, and Maria Joana Soares. We are all from the Math Department of the University of Minho in Portugal. I remember now the algebra of coquaternions. If we have an orthonormal basis of R4, 1 I, J, K, a coquaternion is an element in the span of the elements of this basis. The algebra of real coquaternions, which we denote by H-coq, is generated by the product given according these multiplication rules. Observe that on quaternions, j square and k square equals -1. On the package coquaternions, a coquaternion is an object with head coquaternion, which means it's a function with 4 arguments that are assumed to be real numbers. So we load the package, and here we can define coquaternions like this way. The package teaches Mathematica to work with these objects. So plus, minus, times, non-commutative multiply, power can now operate with coquaternions. Here you can add coquaternions, you can multiply non-commutatively two coquaternions, and we can calculate the square of coquaternions. Considering a coquaternion Q, Q naught is the real part of Q, and this part is which we call the vector part of Q, and we represent Q under bar. The conjugate of Q is represented by Q over bar and equals the real part minus the vector part. Trace and the determinant are these quantities. So the functions on Mathematica that compute the real part, the conjugate of complex numbers, the trace and the determinant of matrices were updated and accept now coquaternion as arguments. So we can verify, for instance, if the conjugate of coquaternion P equals P, and other confirmations. So the focus of this talk are coquaternion polynomials. H x denotes the ring of polynomials P of x, whose coefficients are located on the left-hand side of the variable. The addition and multiplication of such polynomials are defined as in the commutative case, which means that the variable is assumed to commute with the coefficients. A coquaternion is an object with head, a coquaternionic polynomial is an object and the arguments are the coefficients. So, loading coq polynomial toolbox, we can define now polynomials P1, P2, a coquaternion alpha, and we can add polynomials. We can multiply a polynomial by a scalar, or we can multiply polynomials. we define an evaluation map that allow us to compute P of Q. Of course, if P of Q equals 0, then then we say that it is a 0 of the polynomial P. So here are some examples of the evaluation of the polynomial P1 and P2, defined in the last example of evaluated in the scalar alpha, Quaternion alpha. Observe that we can observe that Quaternion minus 2i minus j is a 0 of the polynomial P1. Observe that if we have a factorization of a polynomial, which means if we have a polynomial P that is the left polynomial L multiplied by a right polynomial R, in general is not P of Q is not in general equal to L of Q multiplied by R of Q. Here is an example that shows that if we have the polynomial L, R, and we define P as L times R, evaluating at these polynomials in the Quaternion Q, we observe that P of Q is different from L of Q multiplied by R of Q. We present now some definitions. Quasi-similarity equivalence relation. Two coquaternions are quasi-similar if and only if they have the same real part and the same determinant. We define the quasi-similarity class. The class which representant is Quaternion Q, this way, obvious, and we observe that this class can be identified with hyperboloid in the hyperplane of R4, defined by the condition x naught equal q naught. It is an hyperboloid of one sheet if the determinant of vector part of Q is negative, a cone if it is equal 0, and two sheets hyperboloid if the determinant is positive. Characteristic polynomial. The characteristic polynomial associated with the quasi-similarity class of Quaternion Q is a second-degree monic polynomial with real coefficients defined as is here. Observe that any second-degree monic polynomial with real coefficients is the characteristic polynomial of a quasi-similarity class. If we have a polynomial S with this factorization, then S is the characteristic polynomial of alpha, a complex non-real root of S, and if S has real roots, then S is associated with the characteristic polynomial of the quasi-similarity class of Q, where Q is this coquaternion. We define also the conjugate of a polynomial P bar, equal where the coefficients are the conjugate of the coefficient of P, and companion polynomial is P times P bar. Observe that Cp is a real polynomial. And if the leading coefficient is non-singular, then Cp is a polynomial of degree 2n. Result: if Z is a 0 of P, then the characteristic polynomial associated with Z is a divisor of the companion polynomial of P. In what follow, we will lead only with monic polynomials. So if we have a companion polynomial which factorization is like this, then the characteristic polynomials which divide Cp are associated with these quasi-similarity classes. Observe the zeros of P belong to the union, the union of these classes. So we call these classes the admissible classes for the polynomial P. Okay, an example, we define a function that allows us to compute the companion polynomial of a given polynomial P, and also a function that computes the admissible classes of P. Sorry, we can see that we have if the zeros of the companion polynomial are these ones, so we have two classes. So we present now the theorem that allows us to compute and characterize the zeros of a co-quaternionic polynomial. This result was obtained by us and is published in the linear and multilinear algebra. Very briefly, what this theorem says that if the admissible class of Q, let Q be a co-quaternion, which admissible quasi-similarity class is an admissible class of the polynomial P. Let A plus Bx be the remainder of the right division of P by the characteristic polynomial associated with Q. So we have a different situation. If determinant of P is not equal 0, then there is a single co-quaternion in this class that is the 0 of P, so we call it an isolated zero. If A equals B equals 0, then all the elements of the class of Q are zeros of P, so we call it an hyperboloidal zero. If determinant B different 0 and the determinant of P equals 0, and this equation has solution, that then the zeros of P form a line defined this way, contained in the class of equivalence, and so in this case we call it linear zero. In the fourth case, we also have an isolated zero, and so and if none of these of the above situations holds, then we have no zeros. Okay, so if we want, let's see how can we compute following the algorithm that the previous theorem gives. How does we compute the zeros associated with the admissible class of -2 minus I? So what we have to do, we have to find the remainder of the division of the polynomial P by the characteristic, the admissible class associated with the first element, that element. So we know that B and A in the last theorem are these co-quaternions. Determinant of P is equals 0. So let us see in what situation we fall. First, determinant of P is equal 0, so we are not in this situation. A and B are different 0, so it is not also an hyperboloidal 0. In the case 3, B different 0, determinant of P equals 0, but it's easy to see that this equation has no solution because determinant of the vector part of Q equals 1, so a square of a real number is always non-negative, and we can observe that we fall in situation 4. So in this situation, we associate with this, we have an isolated 0. We can compute this 0. We can ask the zeros of P, and we observe that This function gives a list of 3 sublists. The first list, we have the isolated zeros of the polynomial P. In the second list, the linear zeros, and in the last list, the hyperboloidal zeros. And we can observe that in this situation, we have only one isolated zero. Okay, I will skip this, so I will finish. Thank you very much for your attention.
Well, thank you very much, Fernando. I think that you spent all the time
I'm sorry.
presentation, and we don't have time for any questions. Maybe in the end of the session, if someone wants to ask you something. So I think it's better if you don't mind to stop sharing your screen.
Sorry.
Our next speaker is Gabriel Pazza. I don't know if he's coming from Brazil. I knew that Valdivino was coming, but
Yeah, I'm from Brazil.
yes, from Brazil. He's going to talk about aircraft navigation system safety assessment via probabilistic model checking. Please, you can start.
All right. So my name is Gabriel Pazza. I worked with Valdivino on this paper dealing with safety assessment via probabilistic model checking. So just to cover the general objectives for this work is to demonstrate how formal verification methods such as probabilistic model checking can be used for system safety assessment process, demonstrate how continuous time Markov chains or CTMCs can be used to model equipment failure conditions, pilot decisions, and even flight phase transitions with real world example based on FAA guidance material. So the system safety assessment is a mandatory activity for certification of aircraft complying with Part 25 airworthiness standards. So if you ever flew an aircraft, it certainly has undergone this process to guarantee its safety. There are multiple industry guidelines for this process, including some known methods such as failure mode and effect analysis, or FMEA, failure hazard analysis, or FHA, and fault tree analysis, FTA. In this case, we're exploring some Markov analysis, which are not the classical methods most commonly used, but can certainly be useful for this type of modeling. So in safety assessments, there's typically an inverse relationship between the acceptable probability for a certain event and its criticality. So the more critical an event is in terms of safety effects, the less probable it has to be. You have to demonstrate that it has to be very unlikely to happen. So if you have no safety effects, there's no probability requirements. If you have minor safety effects, there's a higher probability allowed. If you have a catastrophic failure condition, then you have to demonstrate that your system is very robust and has a very small failure rate, smaller than 10 to the minus 10 per flight hour. So in this specific study, we provide system safety analysis or assessment for navigation systems of a generic commercial transport category aircraft following the guidelines from FAA AC 20-138 Delta. It provides some failure classifications for 5 different types of operations, one of which does not have very critical failure conditions, so no quantitative safety assessment analysis needed. So we'll focus on the 4 remaining types of operation, which include some en route and some approach operating procedures. So when the aircraft is nearing the destination, it needs to align with the runway, and the system needs to provide guidance for landing. So the high-level system architecture for the avionics considered in this work is provided here. Have a redundant avionics bus feeding 4 display units on top, and the information provided and those display units is given by a multitude of equipment, including sensors and radio navigation sources, which are redundant. We don't have to go into detail here, but this architecture is something that's considered in the beginning of the design of the aircraft in order to comply with the safety objectives. And each operating condition will use a subset of those equipment. So there's a minimum set of equipment that needs to be serviceable in order to perform each operation. How do we use probabilistic model checking for this purpose, right? So the probabilistic model checking is an extension of a classical model checking, which is a formal verification method based on stochastic transition systems. In this case, we're using continuous time Markov chain models, which are basically transition systems where each transition happens with an exponentially distributed probability over time. So lambda here would be the event rate, and the higher the event rate, the higher the likelihood of that transition to occur. You have a finite set of states that can occur. There's an initial state, and the transition matrix R determines the event rates for each of the transitions that may occur. For each state, there's a set of atomic propositions, or APs, that define whether or not, for example, there's a failure condition in that state, whether or not some operation is viable or capable or not, that sort of thing. So in our specific CTMC model, we're modeling failure conditions for several equipment that go on board the aircraft, and we're modeling 2 different failure modes. It's either failed, or it's an enunciated fault, or erroneous indications, which is a non-enunciated fault. At any given time, an equipment starts as healthy, operating healthily, and then it may either transition to failed or erroneous. And once it's in an erroneous state, it may eventually transition to a failed state. And typically, those failure rates are provided by the equipment manufacturer based on previous experience or internal models of the equipment. So as we see here in this diagram, we have different flight phase exposition times and different contributions for fatal accidents. So even though final approach or takeoff may correspond to a smaller percentage of the time the aircraft is flying, they correspond to disproportionately contribute to fatal accidents. So their fatal accidents are more likely to happen on final approach and landing flight phases as opposed to cruise, for example. So it's important to take that into account when performing safety assessment. So we did do that. We do model the flight phase transitions. So in this case, we can transition from takeoff, climb, cruise, descent. Once we're in descent, if we're capable of performing that operation, we will continue to approach. After approach, we continue to landing if we're still capable, and then we go into pre-flight, which is the aircraft is on ground. If there's a failure that prevents that operation from being performed, we'll not be capable. Therefore, the pilot will decide to go to an alternate approach, followed by landing. Or if that condition occurs during the approach, the pilot may choose to perform a missed approach or go around, then followed by an alternate approach. So this is how Prism works. There's a software that's used for probabilistic model checking. This is how when we model that there, we define each transition and define which what is the probability or rate of that transition to happen based on a typical flight duration of 1.5 hours. For specific operations such as LPV, which is localizer performance with vertical guidance, is a type of GPS-based approach procedure. We define some capability formulas that define whether or not that approach is viable or not, whether or not there's some misleading information to the pilots during that approach. And we define some safety properties for that specific operation based on the classifications given by FAA's AC20-138 Delta. So for a loss of navigation, it's considered a major criticality event. So it needs to, it cannot happen with a probability higher than 10 to the minus 5. And since misleading information is considered a hazardous event, it cannot happen with a probability higher than 10 to the minus 7. So when the aircraft is in a go-around state, it's assumed that there was a loss of navigation or flight phase equal 8. So it has to happen with a probability lower than 10 to the minus 5. And if it's in the approach flight phase, which is phase 5, and there's some misleading information, that would correspond to the hazardous failure condition, which cannot occur with a probability higher than 10 to the minus 7. So the results, basically, the CTMC models for each operation type are comprised of very relatively simple building blocks, as we have seen, but when combined, they describe relatively complex behavior, which is why it's important to use formal methods. So we can see here on table 4 that there are quite a few reachable states and transitions, which are possible or at least not practical to analyze manually by hand. So this is why it's important to use formal methods. So for all operation types and failure modes, we have the classification and the acceptable safety objective, which is 1.5 times the acceptable per flight hour failure rate, which is because we chose a 1.5 hour mean flight time. And on the next column here, we see the calculated probability for each of these events. And as the calculated probability is lower than the objective, we can assert that the system is compliant. It complies with the safety objectives. The models are relatively flexible, so they allow for easy evaluation of impact of design parameters and assumptions, such as in this case, mean flight time. We determined that even though the first assumption is 1.5 flight hours, if we assume a flight time of 18 hours, which is currently the longest flight on record, we still comply. We may still analyze what the impact that has on the probability events over time. So the models are relatively flexible and allow for these types of experiments to be performed. So in order to conclude, we can conclude that safety assessment is an inherently complex, laborious, and critical process. As such, it benefits from adoption of formal verification methods such as probabilistic model checking. CTMC models can represent arbitrary asynchronous stochastic transition systems, which are very flexible. For example, allowing modeling of flight phases, pilot decisions, as well as multiple equipment failure modes, which is good if we're modeling complex systems such as embedded aircraft systems. For future work, one future direction is trying to integrate classical methods such as fault tree analysis, FMEA, and with probabilistic model checking. This can be done, for example, by using probabilistic model checking to determine the intermediate probabilities of subtrees in fault tree analysis. So this can also alleviate the issue of scalability of large models with CTMCs and probabilistic model checking as a whole, and also ease interactions with certification authorities who are invariably more familiar with the classical methods, such as FTA, which is usually what's typically used in the industry. So with this, I conclude my presentation and open to questions.
Okay, thank you very much. I think that you just have time for one small question. Is anyone wants to make a comment or ask a question?
Can I ask a quick question?
Yes.
Okay, thank you for your presentation. It was a really nice presentation. My question is just regarding these safety issues. Is this already implemented nowadays, or this is just something to be implemented in the future, these models that you presented here?
This is something that we haven't implemented in practice. I work at Embraer, so I work in development of aircraft, but I haven't yet used this in practice. I'm sure Markov models have been used in other projects, not by me specifically, but safety assessment, including classical techniques, as they have absolutely certainly have been used in pretty much all commercially certified aircraft that are operating currently. So
okay, thank you.
Oh, thank you very much. I think that we can start next speaker. If you don't mind to stop sharing, yes. Luis, I think you are going to present in the next paper. Yes?
Yes.
Okay, you can share, please.
Okay, just a second. Can you hear me and can you see my presentation?
Yes. So our next speaker is again Luis Ferraz, now in another subject. He's coming from Portugal. He's in Portugal, and he's going to talk about optimization approach for parameter estimation of generalized PTT, Viscoelastic Model. So you can start, okay. Luis, please.
Okay, Professor Irene, thank you for the introduction. As Professor Irene told us, the title of this work is Optimization Approach for Parameter Estimation in Viscoelastic Models. This work was developed by Fernanda Costa, Cecilia Coelho, and by me, and we all come from the Center of Mathematics, University of Minho. And I'm presenting on behalf of Fernanda Costa, Professor Fernanda Costa. So I'll start with the introduction, when I'll present the motivation and objectives of this work. I'll present also some results from viscoelasticity that some of them I also presented before in my previous presentation. Then I will present the governing equations, and especially for shear flows, and I will end with some optimization methodologies and numerical methods, and also the conclusions. So motivation and objectives. So basically, we would like to develop optimization procedure for estimating model parameters for viscoelastic models. In this case, we focus only on shear experiments. And why is this important? Mainly is because these viscoelastic models allow us to model everything we see in our daily lives, like toothpaste, like honey, creation of modeling of food products, or every kind of plastic that you see in your houses. So viscoelasticity, I will divide this in two parts. Classical models, I'll present the most basic viscoelastic model, which is the Maxwell model, and then I'll present a more recent model, which is a generalized PTT model. This slide comes also from the previous presentation that I made, but basically I have the Maxwell model here, and Maxwell model combines two types of movement. This one related to the spring, and this one related to a dashpot. In the spring, we see that if we try to stretch the spring, the stress is proportional to the deformation. Stress is represented by sigma, deformation by gamma, and this is the constant of proportionality. And this means that the more we stretch the spring, the more the stress increases in our hands. In a dashpot, we have a similar behavior, but in this case, the stress is not proportional to the deformation, but in this case, to the rate at which we deform. And we have these subscripts E for elastic and F for fluid. If we combine these two elements, we have what we call a Maxwell model. And if we combine these two equations, you can see the algebra here, we obtain this constitutive differential equation. We have a spring, and we have a dashpot that will compensate for this spring. Here, this figure is just to illustrate how this spring and dashpot interact with each other. Here, we are not exerting any force on the spring or the dashpot, so we see no stress felt in our hands. Then we suddenly stretch, and of course, we feel a stress in our hands because of the spring, and along time, we see that the stress decreases because the dashpot compensates for the spring. The Maxwell model is given in this differential constitutive equation, but this equation has a problem because it's not frame invariant. That means that if you perform an experiment in your house and I perform an experiment here, we won't obtain the same results. So in order to transform this equation to become objective or frame invariant, we need to use some different operators, and mainly the issue comes from this derivative in time. So if we want to generalize this, we will use tensors, and these bold symbols represent the tensors for the stress. Here we have the deformation, and here we have the deformation tensor. This lambda here is related to these parameters, as you can see here. And this symbol here is known as the upper convected derivative. And this derivative is still a time derivative, but now it has different properties and allow the model to become frame invariant. That is, the different observers will obtain the same result. These classical models are often used in the past, and now they are still being used in the present. And the model itself is not able to mimic the real materials, because different materials can have different distribution of molecules that present different relaxations. So a common practice is to use different or a combination of different Maxwell models, or as you can see here, attributing different parameters for each model. So more recently, a new model was developed and presented in the literature, which is quite similar to the upper convected Maxwell model that I showed you before. But you can tell the differences here. We only have this function here that I'll later present what it means. And you have this derivative here, which is no longer the upper convected derivative. It's something called the Gordon-Schwalter derivative, but it's not something of interest for this case here. So imagine that we have a time derivative here. So basically the only difference between the UCM model and this model is this new term here. This new term, this K, is a function of the trace of the stress tensor, which is represented with this sigma subscript KK. And this is related to the network destruction. So I will try to explain now how this works. The upper convected model has some problems because it's constructed based on a spring and a dashpot, but it cannot really represent physically the materials because it allows for infinite extension of the spring, which we know it's not true. So in order to overcome this problem, we proposed this model where we just had this function here. And to understand what this function does, you can take a look at this figure. Here we have some viscoelastic material. This is a picture from honey. And imagine that we have here a viscoelastic material at rest, and I zoom in and I can see here the different molecules. And you can see that the different molecules are connected with these junctions here. As I deform the material, what will happen is that these junctions will be destructed, and also new connections will be performed. So, and this can be verified experimentally that this the rate of increase of these junctions of this function here follows this trend. So in the past, in the 1970s, two models were proposed in the literature where they fitted this curve, which is this function here, with a linear function or exponential function. Of course, the exponential function would provide better results. But we propose a new version of the model where instead of exponential function, we propose the Mittag-Leffler function, which is the model is here for this function here. And the Mittag-Leffler function generalizes, as we all know, the exponential function by adding two extra parameters, which are alpha and beta. So now the governing equations and shear flows. So basically what we want to do is we have a new constitutive model to model viscoelastic materials, and we want to see how the model behaves. And basically when I say behaves, I want to see how the model adjusts to experimental data. But for that, I need to obtain the governing equations for from which I obtain that experimental data. So first, I will present just the governing equations in fluid mechanics. Here we have the continuity equation. So this is basically the mass conservation, nor mass doesn't disappear or is created. Here we have the momentum equation for the velocity. And basically, is the law that says that force equals mass times acceleration. Here we have mass. Here we have a derivative of velocity, so we have acceleration. And here on this side, we have the forces. And the forces that are exerted on a portion of fluid, imagine a viscoelastic material, are the pressure and the stress. Okay, imagine shear stresses. And also, this is coupled with this constitutive equation, which was the new model that I presented before. So you can see that all the equations are interconnected. I have here equation for the velocity. I have here an equation for the velocity, but also I can see here pressure and stress. And here I have an equation for the stress that also depends on the velocity. I won't explain how we solve these equations because this is out of the scope of this work. But I just want you to imagine that since we are going to study shear flows are very simple flows. These equations will be further simplified. And so it's quite easy to obtain analytical expressions. So we will study here two different shear flows. In one case, we will obtain the storage and loss moduli. And in the next stage, we will obtain the shear viscosity. This is the experimental apparatus to obtain this storage and loss modulus. And I will just state the following. Imagine that we have a plate. Imagine that we have here this orange is some viscoelastic material, maybe, I don't know, polymer melt. And then we put on top an upper plate. This upper plate will start oscillating. And the oscillation is given by this formula here, this sinusoidal formula. If we substitute this in our constitutive equation, we will obtain two expressions. One which is called the loss modulus, which I'm showing you here, and one which is called storage. In order to understand how this works, we can imagine a tennis ball. We drop the tennis ball, and you can see that the tennis ball cannot go up to the height that it came from. So this distance here is called the loss, what we lost, and this is the storage, the energy that we could store. And these are the expressions for the loss and for the storage. These are the models that we are going to use to perform the fit. And another thing that we would like to perform a fit to experimental data is the steady shear viscosity. This is more difficult to explain experimentally, but I will just present the formula. So this is our shear viscosity. It depends on this shear stress, and this is the deformation that I will impose. I can impose the deformation that I want. This shear stress is obtained by this formula, but we have a problem here because we cannot just substitute this formula here, because this normal stress, sigma of xx, can only be obtained by solving this nonlinear equation here, which we write in a compact form as the function h. And we will obtain this normal stress for each of the deformation we will impose. So as I showed you before, we can use more than one mode to model our material, and which is the case here. So I will assume that I have n modes, or this means that I will have n constitutive equations. So the formulas that I have to fit to experimental data are this one, the G prime with the head, and I'm summing all the results obtained from the different modes. These are the formulas that I showed you before here. So I have G prime, G double prime, and I also have the formula for viscosity. And these are the set of parameters: alpha, beta, lambda, eta, and G0, and epsilon, and also the sigma xx that I need to obtain from that nonlinear equation that we need to obtain for each of the rate of deformation that we impose. So this means that we have a quite large number of parameters that we need to optimize, and to do this by hand or by heart, it's quite difficult. So it's better to obtain an optimization algorithm. So now we'll see the optimization methodologies and the numerical experiments. Basically, we will fit these models to experimental data. So the first problem is to find these two parameters, lambda and G0. And for that, we define this minimization problem, where we would like to obtain the parameters lambda and G0 that belong to the space Rn. And basically, we need to minimize this function, where we have here the results obtained by the model that we use to fit. And these are the experimental results. And we have G prime and G double prime. So we would like to minimize this function subject to these conditions that we need to impose in our parameters. We have a second problem. Then we'd like to obtain alpha, beta, eta, and epsilon. So we want to minimize this function here. And what we have in this function is the model obtained for viscosity, and here we have the experimental results. So this should go for 1, and then this minimization, this function should go to 0. So, but now in our restrictions, in our bounds, we have a problem, because we need to solve this nonlinear equation for each value of the deformation. So this means that we have involved. We have a big system of nonlinear equations with these.
Luis.
Yes.
Sorry, we have just 1 more minute.
Okay. I'll finish really fast. Okay, sorry. So this is quite difficult to solve, and quite tedious and hard to solve, even in a very good computer. So we will use a different approach for this to solve this problem, which we call sequential approach. So basically, what we start with an initial guess. We already obtained the lambda and G0 parameters from the previous optimization problem, P1. And we will solve first this nonlinear equation sequentially. And then we have this minimization problem, where we have the previous minimization problem, but now we are not subject to that nonlinear function. And we will see if we obtain we achieve our tall or not until we obtain convergence. So now I'm just stating that the problem P1 was solved with EPOPT method. It was coded in AMPL. And problem P2 was coded in MATLAB because we needed to evaluate the Mittag-Leffler function. Just to finish, so you can see here the fit obtained for the G prime and G double prime. We can see that we have very good results, and the fit obtained for viscosity. Here are the parameters, the optimal parameters obtained for the first problem, P1, and here are the parameters obtained for the second problem, and some of the characteristics of the optimization problems. I'm sorry, but I have to finish. So the conclusions: we propose a 2-step optimization procedure. We could estimate the parameters, and we could obtain a very good fit to experimental data. in the future, we would like to perform these in different experiments. So thank you very much, and sorry for my
Thank you, Luis. It's really a pity that we do not have more time to discuss this kind of interesting subjects. Okay. But these are the rules. So I think that we are going to pass to the next speaker. And the next speaker is Azure Evangelisti. I don't know if this is correctly pronounced. Can you share, please?
Yes.
So,
let me know if it works.
Let me just say that she's coming from Italy. Is
yes.
Okay? Italy. Mm-hmm. She's going to talk about 3D simulations of two-component mixes for the prediction of multi-component mixtures Microtexture. This is very long title. Intermediate outcomes. Okay, you can start.
Thank you for the opportunity to present our work, and let me express a special thanks to the co-authors that are the professors Mauro D'Apuzzo, Vittorio Nicolosi, and Daniela Santilli. As suggested in the title, I'll present intermediate findings related to the Microtexture prediction by means of three-dimensional simulation, because in fact this work is part of a larger project which due to time-consuming needs for the simulation is considered still work in progress. And during this presentation, some results already presented in a previous ICCSA conference, but useful for a complete overview of the procedure, will be briefly refreshed. So the presentation is composed of an introduction to the physical problem, then the presentation of the numerical model will be refreshed, then will be presented the experimental campaign of the virtual simulation, then the proposed and theoretical approach for the prediction of the Microtexture of multi-component system will be introduced, and finally the conclusion will be deduced. Let me spend a few words to introduce the concept of pavement texture. In fact, according to the International Standard Organization, the road pavement texture is defined as the deviation of the pavement surface from a true planar surface. And from this definition, the pavement surface can be represented as a profile, which according to the Fourier analysis can be represented by a continuous distribution of sinusoidal curves characterized by different wavelengths and amplitude. And basing on this characterization, it is possible to identify 4 different texture domains that are the macro, macro, mega, and an evenness domain. Why it is so important to characterize the Microtexture domain? Because it directly affects safety aspects that are the friction in wet condition and the splash and spray phenomena, but also environmental aspects as the rolling resistance and the rolling noise. From these reasons, it is important to investigate the possible theoretical links between the Microtexture prediction and the grading and volumetric characteristics of the bituminous mix, but also the compaction techniques and the energy used for the compaction. And it is the main aim of this presentation. The Microtexture can be described by means of the main texture depth index, which is historically evaluated with the sand-batch method. This method was designed to provide an average depth value of the pavement by using a fixed volume of sand, which is spread on a circular area, and the measure of the diameter of this circular area allowed the evaluation of the Microtexture index. As previously introduced, in order to investigate these possible theoretical links between Microtexture prediction and characteristics of bituminous mixes, a numerical model has been designed, developed, and calibrated. There is a laboratory test which allowed to reproduce the real compaction condition under actual road paving operation, and it is the giratory compactor test. In fact, during this lab test, the bituminous pavement is subjected to deformation and shearing force very similar to the real action of a roller during the field compaction. So according to the European standards, the test consists to applying a vertical stress on a cylindrical sample of a spaltic mixture insert in a mold with an internal diameter of 150 millimeters. The longitudinal axis of the mold is rotated at a fixed angle of 1.25 degree respect to the vertical axis and performs 30 cycles per minute, applying a dynamic shear of all the simple phases. In order to reproduce and to simulate this laboratory test, the discrete element method has been selected, and the external geometry is composed of steel mold plate and funnel in shell elements, and the aggregates have been represented by rigid bodies with spherical shapes. In particular, the rheological behavior of the asphalt mixes is described by the well-known Viscoelastic Model called Hertz-Mildel model, here shown. And basically, the behavior of the bitumen is described by dashpots, and the interaction between the aggregates are represented by spring and friction coefficient. The simulation is composed of 4 phases. First of all, the position of the apparatus and the particles. Then the particles are free to fall in the funnel and in the mold to have a random arrangement. Then the plates take the right position and start the final step, that is the compaction and the rotation of the mold. As previously mentioned, preliminary findings have presented in previously conference, so here are just briefly summarized. First of all, after a wall effect analysis, we identify a vertical cut of 15 millimeters along the boundary of the spacement to neglect the wall effect, regardless the particle's radius. But also, we identify a reference depth. In fact, during the simulation of monogranular mixes, we show that a cut at half diameter depth respect to the upper surface of the spacement produce MTD values that are closer or belonging to the theoretical pegging configuration domain, and also allow to reproduce the presence of bitumen between the aggregates. So these two results are fundamental steps for the analysis of the surface and have been included in a MATLAB code for the virtual surface reconstruction and the MTD evaluation. Then has been defined a virtual experimental campaign that is based on a balance between the results validity and the computational efforts. So 4 two-component mixes have been designed with 20 millimeter as bigger diameter, and for each mix, 5 different percentage proportions have been defined, obtaining 20 different two-component mixes. To have an idea, just an idea to the initial arrangement of the spherical particles before the compaction phase, here has represented the 4-20 mixture with 3 different percentage proportion. Here is summarized the ad hoc code developed with aim to evaluate for each simulation the final value of the macrotexture in terms of MTD index by means of the reconstruction of the upper surface of the virtual spacement, starting from the final position of the particles. Here we can see the time history of 3 different mixes, and according to the physical sense and to the outcomes obtained for the monogranular mixes, the macrotexture, expressed by means of the MTD value, follows a decreasing trend during the time. We can see that for the mixture 2016, regardless the percentage proportion, the MTD value and trends are constant and similar, and it can be due to the similar value of the diameters. Then it can be observed that generally the MTD value decreases with the smaller diameter, and in any case, between the percentage proportion at 75% of the bigger aggregates, the MTD value is almost constant and close to 5 millimeters. In particular, this aspect can be ascribed to the segregation phenomena, which is strongly visible into the 24 mixtures, where the dimension of the particle is more accentuated. Other conclusion can be done, in fact, adapting the void content representation of 2 component mixes to the macrotexture representation. It can be seen that for the same percentage, MTD values decreases as the DD ratio decreases. In particular, for each component mixes, a decreasing trend can be seen as the diameter of the fine fraction decreases, with an increasing accentuated slope. And this concept is evident by observing the table. In fact, a linear dependence can be found between the DD ratio and the angular coefficient for all the 4 analyzed mixtures. On the other hand, the intercept value can be considered as a constant. And from these premises, the expression of the macrotexture predictive model for multi-component mixers was designed, developed, and here summarized. First of all, starting from the multi-component mix, divided it into subgroups of 2 component mixes, standing from the finest 2. For each subgroup, applying the void content diagram representation and evaluate the MTD value corresponding to the percentage of the finest fraction, considering the subgroup as a monogranular mix characterized by an equivalent diameter. Then these same steps have to be repeated until the final group is analyzed and the final value of the MTD is obtained. On the paper, a numerical example has been provided, and if you are interested, after the conclusion, we can show an application of the method. But let me conclude that this work is a part of a larger project, which included results obtained on monogranular mixes and used for these applications. Here, a virtual experimental campaign on 2 component mixes have been designed and performed, and the relevant results have been obtained as the confirmation that the TEM simulation is an effective tool also for 2 component system, but also that the MTD values follow the decreasing trend as a fraction of the fine particle increases with respect to the coarse particle, especially when the DD ratio decreases. And on this basis, a novel theoretical approach for the prediction of the macrotexture of multi-component mixes based on the void content representation have been proposed. So we can conclude the void content diagram applied to the macrotexture description and prediction seems to show encouraging outcomes. Thank you for your attention.
So, thank you very much for your presentation. I think that we have time just for one small question or comment. Is there anyone that wants to ask something?
Can I ask one
Yes,
question?
yes.
Really fast question. Thank you for your presentation, a very good presentation. I just would like to ask, you were saying that you use the discrete element method to perform the simulations. My question is, you only use the particles, or you also model the bitumen part, or?
Using the Earth-Mindel mechanical quantitative model, we try to model both the bitumen behavior by means of the dashpot, but also the aggregate interaction, of course.
Okay.
Then, during the previous simulation regarding monogranular mixes, we, after the simulation, so in the post-analysis of the surface, identifying the, identifying the reference depth, we also take into account the presence, the physical presence of the bitumen between the particles, applying this horizontal cut.
Okay. And for example, to obtain the parameters for that model, is it possible in laboratory to perform physical characterization of these parts?
We did this. The effective calibration of the model by means of simulation of real spacement in monogranular example.
Okay.
Yes. We applied this in the lab with a giratory compactor.
Okay. Thank you.
Thank you.
Congratulations.
Thank you.
We cannot hear you, Professor Irene.
So I'm sorry. It's lunchtime. So I would like to thank all the speakers in the morning. Our session in the afternoon starts at 3:15. And since we just have 3 speakers, I think that we'll have opportunity to discuss some of the presentations in the morning and ask some questions to the speakers if you want, okay? I'm sorry for not giving you the time that you wanted, that we want to have the opportunity to discuss your work, but okay.
Thank you.
Bye-bye.
Thank you.
Bye-bye.
Bye. Thank
Have a
you.
good lunch.
Thank you. Bye.
Bye.
Thank you.
Acho muito chato. Acho muito chato não se poder. Não acha?